Alright, so this is section 4.6. Yes. Where we're doing some graph sketching and asymptotes. And sort of the things that we're going to be doing here is this. We're looking for zeros. Anywhere there's a zero, we're going to graph those. How do we do that? Well, we're going to be given a function. We're going to take that function, we're going to set it equal to 0. Okay, now that's nice if you can do it. Some functions are easy. Some functions are gross. It's going to be hard to do that. But that's a big deal. We're going to be looking for extrema. Extrema, what does that mean? Well, we're going to be looking for where's the first derivative equals 0. While we've got that first derivative, remember, if this is a critical value, that is where the derivative is 0, the derivative might be negative on one side and positive on the other side. If that's true, that means it was coming down and then going back up. That means this guy was a minimum. So where is the thing, where is it concave up, or where is it increasing or decreasing? We're going to look for where is it concave up or concave down. Concave down, concave up. Obviously points of inflection when it's equal to 0. Okay. We're also going to be looking at what happens if there's an asymptote. Does it go up? Does it go up? Does it go down? What happens? What happens is you head towards infinity. Does it go to 0? Does it go to negative infinity? Whatever. What does it do? So that's the sort of things we're going to be looking for. I'm going to stick with some easy ones like your book asks you to do. I do that because, well, they're nice. On a test, I might make you have maybe a little messier one, and you're going to, maybe you'll be upset, but that's okay. You'll probably get over it. But if I give you a harder one, I will make it so that it's not that horrible to do, and I'll show you what I mean by that. All right. Now it says this: we want to sketch the function. We want to indicate transition points where there is maxes or mins or points of inflection. I would argue that also I'd like to talk about zeros while I'm here. I'd also like to talk about what happens as x gets huge. So right off the bat, I like to look at the zeros. This one's easy. You can factor an x cubed out of it. That leaves you with an x squared minus 5. And so either obviously x is 0 or x is equal to plus or minus the square root of 5. So here's my graph. Square root of 5 is right here-ish. Here's 0. Negative square root of 5-ish. That's what's happening. That's where my functions are equal to 0. Now, I'm going to take my first derivatives. First derivative is 5x to the 4th minus 15x squared equals 0. Take an x squared out. Heck, take a 5x squared out. That leaves you with x squared minus 3. So 0 plus or minus the square root of 3 is where you would have maximums or minimums. Now personally, I do that on a separate sheet over here. I come over here to this is 1.73. 1.73, that's the square root there. Now, I'm going to pick numbers that are out here, like say negative 10. If you put negative 10 into this guy, that's going to be 100 minus 3 is positive. This is 100 times 5, that's positive. Positive times a positive. Positive slopes out here. Now, if I was a betting man, if I put in a number between here and here, I'm going to say they're negative, but let's just see. If I put in negative 1, that's going to be positive. It's going to be 1 minus 3 is negative. Negative times a positive is a negative slope. Okay? I'd be willing to bet that they are positive. Ooh, I lied to you. These suckers are negative. I was thinking I was on top of it, but I'm wrong. 1 squared is 1 times 5 is positive. 1 minus 3 is negative. Negative times a positive is a negative. And then if you put in like positive 5, you will see you get positive slopes out here. Now what does that mean to me? It was positive slope. It got to the top. It came down. We know that when we got here, we had 0 slope. So that means it kind of petered off like this, right? But it didn't go back up. It continued on down. and it came back up. So my function, 1.73 is here-ish, and here-ish. What I know the function must look like is it must look something, give or take, like this. Now you're like, but Jay, you idiot, we have zeros here. You're right, we do. It's got to go through the 0, come up and crest right there. Come down and go through the 0, but have a 0 slope while doing it. So kind of come down and then peter out like that. Go down some more. Negative 1.7 or 1.73, and then back up through 2. Yay! Now, second derivative, of course, talks about my points of inflection. And so, of course, if you factor an x out of them, you're going to get 20, well, you can factor 10x out. There you go. That'll give you 2x squared minus 3. So right here, x equals 0 is a concavity point of inflection. And then x squared is equal to 3/2. So x is the square root plus or minus square root of 3/2. Square root of 1.5 is like 1.2-ish. So 1.2-ish, so somewhere in here, it goes from being concave down to being somewhat concave up. So concave, somewhat concave down, and then right here at 1.2 starts to be concave up. And it's concave up until it goes through 0, then it's concave down. Here at 1.2 it begins to be concave up again, and then up she goes. While I'm here, I'm going to talk about this. What happens? What is the limit of this function as x goes to infinity of x to the 5th minus 5x cubed? Well, as you go this direction, your y's are going up. It's going to infinity. And ditto on the other side, except going to negative infinity. That's the sort of thing you'll be asked to do in this section of sketching. Okay? Let's do another. So y equals ln of x squared plus 1. Yep. All right. So first things first, okay? First things first, when I look at this problem here, I think, all right, well, let's take the derivative. And you're saying, why did you do that first? I don't know, I just felt like it, I guess. So the derivative is 1 over the inside times the derivative of the inside. So my derivative is 2x over x squared plus 1. Now check this out. I could have set it equal to 0 right off the bat. The deal is that when x is 0, this is 1 in here, and the ln of 1 is 0. Okay? So we'll keep that in mind. Now, this is y prime. I'm going to set it equal to 0. What value of x makes this guy 0? Well, it turns out that when x equals 0, that is when the numerator is 0, you get a 0. So x equals 0. This means this is a max or min. Again, how would I know? Here's 0. Pick a value that's less than 0. Say negative 1. 2 times negative 1 is negative. Negative 1 squared is positive, plus 1 is positive. Negative divided by positive is a negative slope. If you put in a positive x like 5 or something, this is positive. This is always positive. Positive slopes. So it was coming down, and it turned and went back up. Now that tells me that on my graph, I knew that at 0 I had a 0. And I know then that it must be some sort of a minimum. Now I'm not exactly sure that's what my graph looks like, but it's something like this. Now, of course, I could take the second derivative as well. Why isn't my pen working? Y prime, double prime, is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So that's 2x squared plus 2 minus 4x squared over x squared plus 1 squared. Set it equal to 0. Well, remember, that's when the numerator equals 0. So negative 2x squared plus 2 equals 0. So 2x squared is equal to 2, which means x squared is equal to 1, which means x is plus or minus 1. That means to tell me that's where my points of inflection are. So again, 0 here, it's got negative 1, positive 1. So I need to put in points. I need to put in points into this equation, into this y double prime equation, and see what I get. First thing I realize, the denominator is always positive. So all I'm looking at is the numerator. So for instance, if you put in a number over here, let's say like negative 6 or something, negative 6 squared is 36 times 2 is negative 72 plus 2 is negative over a positive. So we have negative second derivative over here. Okay? In between, for instance, 0, put 0 in there, you're going to get 2 over a positive. So we have positive second derivatives in here, the whole region. And then if you put in a number like positive 6, you get negatives out here as well. Now what does that tell me? It tells me I do my picture wrong. Because between negative 1 and 1, the thing should be concave up. That looks good. From there to there looks good. It's from there out, it should be concave down. So this is what more like my graph should have been. Looks more like this. Okay? Now, of course, I could go sketch that and see what it looks like. I can ask the Desmos to check it out. Obviously, I don't want you to do them in Desmos. I mean, that's obviously because I want you to practice figuring some of this stuff out. Oh, look at that. It's as if Jay drew the picture correctly. Yay me. Okay? So, that's some of that. And then you'll also be given a couple of these. You're like, you know, this doesn't look that hard because we talked about limits at infinity. And so these ones talk about find the end behavior or find the limit as you approach infinity. And so it's the limit as x approaches infinity. Well, we've done this. We already know how to do this. I showed them to you previously. All right, the highest power of x in the denominator. So on top, I'm going to get 5x over x cubed minus 9 over x cubed over 4 minus 1 over x cubed. Take the limit as x goes to infinity. These pieces both go to 0. So you get 0 on top. This piece goes to 0. So 0 over 4, which is 0. Okay? So it doesn't hurt to review that. There's a few problems, I think, on the homework this week like that. Again, I don't get to choose the homework because this is kind of more of a collaborative class at PSU. This online and everybody else, they all try to make sure we all give the same online homework assignments. If it were my class in the classroom, it might be a little different story, but that's how they want us all to do it, which is fine. So I'm covering some of this stuff because there's a few of those kind of problems on the homework. I probably wouldn't have assigned it in this section. I would have just assigned it in the previous section when we covered that before.